In this video, I'm going to be going over an introduction to the different types of MSI devices. So MSI devices are integrated circuits, like the ICs we've been working with so far. The main difference is that these are combinations of different types of AND, NAND, NOR, OR gates, all these small-scale devices to create a specific application or a specific device. So kind of the analogy that I usually use is that if you think of transistors as being the atoms, the smallest particles in electronics, the next level up, which would be molecules, would be logic gates. They're combinations of transistors and other devices. And then the next level up, I don't know what that would be, an organ maybe, would be MSI devices, which are composed of lots of SSI gates. And we'll look at some of these circuits and what they look like under the hood. But for now, what we're going to do is kind of treat them as black boxes with inputs and outputs and look at the functions of each of these devices. Now, what's important is that there's some terms that I'm going to use here. And for example, this might be, for example, some kind of logic MSI device. And there are always going to be some number of inputs and some number of outputs. But the types of inputs can be either one of two types. Those two types are binary and discrete. So let's say, for example, we have some kind of logic device, an MSI device, and there are four inputs here. We'll call them A, B, C, and D, and the output is X. Now remember, this isn't just like an AND gate or an OR gate where you only have a simple circuit. There are lots of different devices inside here. So we're going to look at these two different types of devices, or inputs rather, and we'll start with discrete. So for discrete inputs, it means there's only one input on at any time. So for example, A could be on, or B might be on, or C, only one at a time. Now, it may mean you could still have potentially multiple inputs, but only one is going to be acknowledged. Now, it's not always logic or positive logic. In some cases, these inputs are going to be negative logic. And you're going to see that a lot of these devices have negative logic. And in that case, what you'd have is a 0 as being an input selecting that input A. So those are discrete inputs, only one input on at a time. So for binary inputs, which may seem a little bit more logical, is we can have any combination of these inputs on or off. So you could have, for example, something like 0, 1, 0, 1, and that would be a valid input. In fact, you could have any input combination from 0, 0, 0, 0 to 1, 1, 1, 1. And so for binary inputs, that's any combination of inputs. And we'll actually see that the outputs are the same way. Some of these devices have discrete outputs, which means only one output is on at a time, or they can also have binary outputs. So if you don't understand that, make sure you review that to understand it, because we're going to be talking about that quite a bit. Okay, the first MSI device we're going to talk about is an encoder. So an encoder is going to take four individual inputs, which are discrete inputs, labeled A, B, C, and D, and provide a binary output. So this is kind of an interesting circuit. I'm going to show the inputs as, in this case, logic 1 or positive logic, 1, 1, 1, 1, like that. So remember, again, with discrete inputs, you can only have one input that's really valid at any time. I'll go ahead and fill in the rest of these with zeros. Okay, and the outputs then are going to be a binary value that represents which input is on. So for example, in the first case, the outputs would be 0, 0, and then 0, 1, 1, 0, and 1, 1. So what we're doing is encoding. That's the key here. We're encoding discrete inputs into binary values. Now, what might be an application for this? Well, if you had, for example, a bunch of switches and only one switch was on at any given time, old school maybe keyboard or something like that, we could encode all of those inputs to a very small number of binary outputs. So here you only are going from 4 to 2, and this would be probably called a 4 to 2 encoder, 4 inputs to 2 outputs. But if we start expanding this, for example, if we have 16 inputs, we'd have 4 outputs, 32 going to 5. So very quickly we can encode a lot of individual discrete inputs to a relatively small number of binary values. So this is an encoder. Now below what I've shown here is an 8 to 3 encoder. 8 inputs, 3 outputs. And instead of drawing 8 individual wires, a lot of the times this is represented as a bus. Okay, so that horizontal line with a little slash through it represents, so that would actually be 8 different wires. So we might have, for example, input 0 all the way to input 7. And then the output here would be output 0 all the way to output 2. Okay, sorry, that's a little hard to see, but hopefully you get the idea there. And so that saves us a lot of wiring, because a lot of the times these are connected to some other device here, which also might have a bus output of 8 bits that we're encoding. Now, I've also added what's called an enable input. This is very common on these devices. And an enable, basically, in this case, it has a bubble on it, which means it's active low. So if this was connected to ground, it would allow those inputs to go to the outputs to be decoded properly. But if that input was high, if we took that to 5 volts, it would not decode those signals. Sometimes the outputs would actually be set to floating. We'll talk about that later. That's sometimes referred to as tri-state. And you might think, well, why would you want to do that? Why would you want to enable that? Well, we could have another encoder here that's looking at another 8 sets of data, 8 bits of data, and we can literally tie these 2 sets of lines together. And then what we could do is, if we used an inverter here, this is getting a little complicated, but if we had an enable here and an enable here, we could have a way of selecting which of these devices, in this case I'll call it A and B, which of these data sets are being routed to the output, depending on whether this control input here is a high or a low. So for example, if this was high on the input, that output would be disabled because it's active low, but this one would be enabled. So that means that the B data would be transferred to the output. If the output was low, this one would be enabled, but this one would be disabled. So we'll talk about that in more detail later, but the enable outputs are very common on these devices. The next device we're going to look at is a decoder. And this is the opposite of an encoder. Now we're taking a binary input. For example, we could have 0, 1, 0, which is the equivalent of binary of 5. And what that would do is turn on this output 5 as a high, for example, in this case, with all the other outputs low. So this device, again, is taking a binary input, anywhere from 0, 0, 0 to 1, 1, 1, and it will only decode one output on at any given time. So let's look at another example. What if these outputs were 1, 1, and 1? Well, that's in binary, it's 7, so output 7 would be 1. And all the rest of these outputs would be 0. So this is just a simple decoder that's taking the pure binary data into discrete outputs. But another common kind of decoder would be, for example, a 7-segment decoder. And that's actually what's used on the little board, the LED display driver board. In this case, we'd actually have 4 inputs here, A, B, C, and D. And the output then is being decoded to turn on different segments on the LED display. Now, at some point, we'll probably go through the exercise of how to use a K-map to actually do some of the mapping on this. A lot of the times, the way this data is written is like this: D, C, B, and A, with the least significant bit being on the right. So, for example, if we decoded this 0, 0, 0, 1, whoops, lost my B there, and had these inputs like this, low, 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 high, it would decode a 1 as the output. So it would only turn on these 2 segments on the LED display. So this is an example of a specific kind of decoder. in this case, a 7-segment decoder, which is what we typically think of when we're looking at LED displays. Now, when I was working in the robotics industry, there's an actual application where I had to use an encoder and a decoder. And we had what was called a control pendant, looked like this, a box here, and it had a rotary encoder and a bunch of buttons on it. And we had a very expensive cable because it was flexible, a lot of conductors, high reliability cable that went to this big control box that ran a robot. And there were literally, I think, 16 wires going through this cable. But then they said, well, we actually want to add 2 more buttons to this thing. Actually, it's 3 buttons. But they're running out of wires. So what I ended up doing was using an encoder on one end to take all these extra wires in, and then ran only 3 wires all the way to the control box, back through a decoder to get all those inputs kind of reconstituted, as it were. So any one of these inputs can only be pressed at one time. You couldn't press more than one at a time. But any one of those inputs would create a binary value that would then be decoded to an individual output here. The advantage is that instead of spending another $500 or $600 on a new cable and having to rewire it, we were able to use just 3 extra wires that were inside this cable instead of all these extra wires. So that's one simple application of encoders and decoders. Okay, the next MSI device is the multiplexer, sometimes called a MUX, or also called a data selector. This is one of my favorites. It's kind of a cool device. What it does, in words, is it will take these 4 discrete inputs, so only one can be on at a time, and based on the binary select input code, it will route that input to the output. So, for example, if select A and B were both 0, it would route A to the output like that. If select A and B were 0 and 1, it would then select B, and so on. So that if both were 1, it would take D and route it to the output. These are probably one of the most useful devices, and in almost any really major logic systems, multiplexers are used a lot. A couple of things of interest: sometimes you have an output that's a true output, and sometimes you have an output that is inverted, output not. And also they can have an enable input, which could disable this data selector compared to another one. Now here's an example of what would be an 8 to 1. Sometimes they show it as an 8:1 multiplexer. And here we have 8 inputs. Now I'm drawing this as a bus. So we'd have input I0 all the way up to I7 as all the possible inputs. But in order to select any of those inputs, we have to add another select input here. So again, binary inputs here, discrete inputs here, and whatever input we're mapping based on the selects is going to be connected to the output. You can think of it, another way you can look at it is like a rotary switch, where you're selecting multiple inputs going to one output. But instead of it being manually controlled with your hand, you're using those select inputs to control it. So as you might have guessed, if there's a multiplexer, there's also a demultiplexer. And this is it's basically the opposite. Now we have a single input, so it's neither binary or discrete. It's going to be either a 0 or a 1, and it's going to route that data to one of 4 possible outputs, depending on the select inputs. So, for example, the cool thing about this is we could have, for example, some digital data, pulses coming in, and we could route that data to 4 different devices, depending on the select inputs. So if select inputs are both 0 and 0, it would route that data, those pulses, out to output A. If it was 0, 1, it would route it to B, and so forth. So demultiplexers are useful for routing a single input to multiple outputs. Okay, next device we're going to look at is what is called a comparator. And a comparator simply looks at, sometimes this is called a magnitude comparator. We're looking at the magnitude of the values between A and B. So, in this case, we have 4 bits coming in on A, 4 bits coming in on B. These are binary values, and 3 outputs. A is greater than B, A equals B, A is less than B. So, as a simple example here, if A was 1 and B was 4, for example, then this output A, whoops, sorry, wrong way, A is less than B would come on, because A is 1 and B is 4. If they're equal, then you have a single output that would come on if they're equal. We'll get to play with one of these in a couple of weeks. In some cases now you'd think, well, if we want to compare more than 4 bits, we'd have to connect multiple devices together. And to do that, what you end up doing is adding another 4-bit comparator, but there's some control output lines that are then connected to the next comparator. And those are used to basically take these inputs so that you have one single set of A equals B, A is less than B, A is greater than B outputs. We probably won't look into that into a lot of detail, but we will look at a simple comparator in the coming weeks. Here, next device is a counter. And a counter simply is counting how many pulses are coming in. And each time a pulse comes in, we're going to increment the output on any of these binary outputs. Like a lot of these devices, there's also an enable input that's common. Sometimes there are multiple enables. The 2 common types of counters are binary counters, which would simply put out a binary sequence. So as each pulse rises and falls, you'd see the outputs increment in binary. A Johnson counter is a little bit different. It is more like a discrete output where only one output comes on at a time. Now there's some really old school parts that we'll probably be using for these. The 4040 is a binary counter. The 4017 is a Johnson counter. We'll actually be using the 4040 in the lab this week. But counters are very common devices used more in sequential logic, where we're looking at something that's based on a clock input. Okay, and finally, the last device that we're going to talk about is a latch. And I forgot to mention this in the last little video clip, but when you see this kind of triangular, sideways triangular symbol, what that means is that's typically a clock or a pulse input, as opposed to just a regular input. So what a latch does basically is it takes data in, and in some cases it will just transparently, what they call a transparent latch, the data from the input goes directly to the output. But if we, for example, put a pulse in here, it will take whatever data was at that moment in time that pulse was going high and store it in a register internally inside the device, so that if the input data changes, it'll keep that data stored and latch it on those output lines. And again, a lot of these devices have enable lines, okay, that control whether or not that output is open or tri-state, or if it's actually the ones and zeros. Now, I'm going to very, very briefly describe tri-state to you. The idea is this, is that if we want to share multiple sets of outputs on multiple lines, we can't just connect them together. We can't take, for example, let's say this is a latch here. We have 8 other inputs. I'll call this data, for example, in this case, this is data A, and this is data B coming in. We would never want to just connect the outputs together. Well, why not? Well, what if output 1 in one case is a 1 and the other output is a 0? Well, that could damage the outputs of the device. But what if we had, for example, data coming from one device and we wanted to be able to select which sets of data are being output? To do that, what we can do, and I'm going to simplify this quite a bit, is that usually we talked about this kind of totem pole output on our gates. Usually we have a PNP transistor on the top of an output, going typically like to a diode and a resistor and then an output pin. And then we go to another transistor that's connected to ground like that. And this side is connected to plus voltage, and this is ground. So that if either one of these transistors is turned on, we can either do what's called sync current. For example, if this one was on and this one was a 0, current from this pin would go to ground, and the output would be a 0. Okay? However, if we turned on the top transistor here and turned the bottom transistor off, now this transistor is turned off. It's like there's a break in the connection, and the current flows out, which would be a 1. Okay? So that is called sourcing current. When current is going out, it's called sourcing. When current is coming in, it's called sinking, when it's coming into ground. And so far on all the logic devices we've talked about so far, only one transistor can be on at a time. If you turned on both transistors, you could damage the output. That would never happen. However, what if we could turn off both transistors? What would our output look like? Well, it'd literally be floating if both transistors were off at the same time. You think, well, that doesn't sound good. That's not a 0 or a 1. And sometimes they'll call that like an X or a Z for high, not usually X, that's don't care, but a high Z output, which means it's floating. So this is kind of a little bit of a diversion. It's more related to the hardware chapter. And if you look up tri-state outputs, you'll see a little bit more information on this. But the point is that this allows us a way of, if we take one enable line that's high true and another enable that's low true and connected those together, we could then basically decide which of these outputs is on at any time. So we could store some data in this one and turn it on, while this one is disabled, and so basically it disconnects that output. Then if we enable this, we stored some data in here, a bunch of 1s for example, and enable this output but disable the top output, then the data would go here. All these would be connected together. If we enabled them both at the same time, that would be a problem. So that's one thing in the design we'd have to be careful about. So that's a little bit of a diversion, but tri-state is important, especially with digital logic systems where we have a lot of data coming in a bus that needs to be sent from one point to another without interfering with other data. Okay, now those are the primary MSI devices. There are a number of others. We probably won't go into a lot of detail on, but there are lots of other kinds of devices. But these are the ones that are the main building blocks of most digital circuits. And we'll be using a number of these in the upcoming labs.